Okay, let's press on with this utterly not confusing floating point representation. Okay, so here's these two bit strings that I had on the slide. Let's see if we can convert them to decimal numbers. Right, this one, first one's easy. The sign is 0. The sign bit is 0, which means that sign bit is 0. In other words, we're talking about a positive number. For the second one, the sign bit is 1, which means we're talking about a negative number. So straight away we can work that out. All right. Maybe the fraction is easier to deal with. Okay, now that fraction that we've got there, remember that represents the bits after the decimal point. So we've got a whole lot of zeros and 1, 1. If you remember what I said before, 1, 1 after the decimal point is half plus a quarter, so it's 0.75. So the fraction part is 0.75, but remember that there's an implicit 1 that's hanging around that isn't stored here, and so we need to add that in. So in fact, we end up with, when we add the 1 in, we end up with 1.75. All right, now the exponent. That, to me, looks like 128, probably. 1, 2, 4, 8, 16, 64, 100. Wow, 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 4, 8, 60, 32, 64, 128. Yes, it is. Wow. All right, so 1 followed by 7 zeros is 128. I should know binary off the top of my head, like you should. We're going to have a speed question in the final exam. It's going to flash up a binary number and you've got to straight away tell us what it is. No, we're not going to do that. All right, so now remember that this thing here represents basically the fraction multiplied by 2 to the power of the normalized exponent. Okay? And remember that I said the exponent is always written relative to a baseline, which is minus, in this case, minus 127. So in this case, the exponent that we're actually dealing with is 1. 128 minus 127 is 1. So we're dealing with the fraction multiplied by 2 to the 1. So that, well, 2 to the 1. So that obviously gives us 1.75 multiplied by 2, which gives us 3.5. So that bit string up here is a representation for the number 3.5. And so I should say, so we normalise. So that's what we're doing there. So, like I said, here we want to, obviously we want to be able to represent negative exponents because we want to be able to talk about small numbers, close to 0 numbers anyway. And so we need a way of representing negative exponents. Now, we could have probably done something like 2's complement for these 8 bits. But for some reason, IEEE decided that what they were going to do, and no, off the top of my head, I can't think of a reason why they would have done it this way. Can anyone give me an explanation? No, but anyway, what they decided to do was to write the numbers as always positive. So they're going to take those 8 bits and just treat it, if you like, as an unsigned byte. Get a value there. The way that you can represent negative values is if you take that unsigned byte and you subtract the maximum negative value, which is 127. So that's the way they decided to represent it. So if you've got 128 in this 8-bit quantity, and it's relative to a baseline of minus 127. What you've actually got is 1. Right, let's have a look at this next one. I should have done the fraction first. This fraction is dead easy. It's 0.5. Obviously, I think there's only 1 bit after the decimal point. But of course, there's an implicit 1 in front of the decimal point. So, if you like, the base part of the number is 1.5. The exponent is this annoying value here, which I will now have to calculate. Let's see, so that was 128, 64, 32, 96. Must be an easy way to do it. 127 minus 1. Sounds about right. 126. Then. Hope that's right. Oh, it's too hard to... Is there a nice way I can do it? Yeah, there is a way I could do it. If I can't be bothered sitting down doing the calculation, let's do it in C. Right, so first thing, I can't write that as binary in C, but I can write it as hex. And the hex will be 0x7 followed by 111 E. Okay, so how did I get that? I split it into 2 4-bit chunks. First one is obviously 7. Second one is obviously E. That's part of your time trial in the final exam. Alright, so what I could do, I could assign that to in fact, it probably doesn't really matter. Since it's only a byte, let's make it an unsigned char and then print it out as a number, as a decimal number. And it might help if I gave the variable names. And it might help if I close my braces. Someone was complaining that I haven't been making errors in programs. Yeah, I could. I should have, just so we can see. Let's leave that out and see what happens. Bang! Expected identifier or parentheses. Good, all right, so there should have been a variable name. That's obvious. Implicitly declaring library function means I forgot to hash include something. I didn't hash include standard IO. And that last one, it's even telling me include the header standard IO. Format specifies type int, but the argument has type dependent type. Alright, in that case I might take the easy way out. Oh, you reckon? Okay. Yeah. Let's see, what else could I do? Nothing. One reason why I don't make mistakes is it takes time to fix. Alright. So, 126, that's what I said. Good. So I have independent confirmation of the value. So this value here is 126. We subtract 127 because everything's relative to minus 127. Therefore, that exponent so the exponent is minus 1. Therefore, the overall number is going to be the fraction multiplied by 2 to the exponent, which is -1. In other words, 1.5 over 2. In other words, 0.75. And since it's negative, then of course we stick a minus in front. So that bit string there represents minus 0.75. If I did all that correctly, you might want to go and check at some point. So the trick is the exponent is always relative to this, what they call bias, which is a negative number, and the fraction part is always the part after the decimal point when we've got a single one in front of the decimal point. So we have to add that one back each time. Alright, anyway, that's floating point for you. Okay, so that'll do for floating point. We'll have some more examples of that in the tube next week. Arrays. Okay, we hopefully know all about arrays. Arrays consist of a sequence of elements. All the elements are the same type. They can be any type. You can have an array of ints, an array of chars, an array of structs, an array of arrays if you really want. So the elements are laid out one after the other in memory. So now remember we're talking about data representation. So how are all these data structures laid out in memory? So here, if we've got an array of integers of length 4, then imagine this is the address. Now we know that can't be a valid data address, but I just chose a small number because if I chose big numbers, they make the diagram messy. But the point is, if this is the starting address of the array, then the next int is going to be located at that address, and the next int element of the array is going to be located here, and so on, and there's only 4 of them. So anyway, the point was that elements are laid out one after the other in memory, and if you've got a pointer to one of these elements, you can move from one element to another by using pointer arithmetic. So you can, obviously we know you can access individual array elements via indices, and that the total amount of space is going to be equal to the number of elements multiplied by the size of each element. If you write down just the name of an array, what it always gives you is the address of the first element of the array. So those two expressions there, if you like, are equivalent. And I think you can even write %v and it will give you the same value. If you just treat the name of if you just write the name of the array, then you can almost treat that as being like a pointer to the elements of the type that are stored in the array. Indexing on most machines I've seen, and that's why I wrote approximately equals, because there may be some other machines that do it differently, is done by taking the base address of the array, adding I, so remember we're effectively doing pointer arithmetic here, so it's going to take you to the ith element of the array. It'll give you the address of the ith element in the array, and then we dereference it with the star operator. So when you write that, that's really a nice form for that. If you've got a pointer just to the first element of the array, you can treat that like a way of accessing the whole array. And strings are really just arrays of chars with a null at the end. And you better make sure your string buffers are big enough to hold the null as well as everything else that you want. All right, so when you pass an array to a function, you're not actually passing the array, you're simply passing a pointer to the first element of the array. So if I've got a main program like this, string 5 is set up to contain the characters A, B, C, and implicitly a null character will be added on the end. And if I then call a function with this, so remember, writing the name of the array kind of is like writing the address of the first element in the array, so effectively it's giving you a pointer to the first element, which I can pass to here, and I can then iterate through the array simply by doing pointer arithmetic. So S is going to get a pointer to the first element, then it'll be set to a pointer to the second, to the third, and so on. One thing that, I don't know, maybe sometimes people worry about when they see something like this is, aren't you messing up the array? Because you're doing S++ and S is a pointer to the start of the array. That may be true. Well, it's not true that you're messing up the array. str is unchanged because all you did when you made this function call was pass the value, copy the value of str into the parameter S. And I think I said it once before that parameters are kind of like local variables, except they start with an initial value which is passed in from whoever called the function. So here it's effectively we've got S is assigned str, and then we do that code there. All right, any questions on that code? Good. One other interesting thing about this that I discovered yesterday, and maybe it's on the next slide. Ah, yeah. All right, these things. Okay, so these are all different ways that you could initialize a character array, but they are subtly different. Some of them are the same, but some are different. So, this second, let's start with the second one. The second one says B is a pointer to a sequence of characters terminated by a null which lives somewhere in memory. Constant strings like this, except when they're used in an initializer like that, are located in the data segment. Okay, we have code, data, heap, stack. So that A string is going to be put just above the code segment, and when I say char star B is assigned that, what I'm actually getting is a pointer into the data segment. Let's now go to this one. So I'm defining an array containing 9 char values, and here I'm using the standard array initializer, which you can also use with ints or whatever, and I'm basically assigning to the individual characters of that array. So C0 gets A, C1 gets blank, C2 gets S, and so on. Okay. So hopefully that's reasonably straightforward. This one here turns out to be exactly the same as writing this. It's just obviously a bit shorter. So writing this as an initializer doesn't give you a string in the data area. What it does, it populates this character buffer that you're defining somewhere. Could be a local variable, could be a global variable, whatever. But it initializes the contents of this array to the individual characters in this string just like that does. And this, I have a feeling, might be illegal. So you can try playing around with those kind of things just to see. So it's always, I've spent ages the last few days writing little C programs just to see where all this stuff ends up. In fact, I might even have one for this. I don't know. What's this? Aha! I do. All right, maybe the last one isn't illegal. No, it is, okay? So that last one doesn't work because this kind of initializer assumes that you've got some space allocated that you're placing the values into. This doesn't allocate any space except the 4 bytes to hold an address. It certainly doesn't allocate a memory buffer for holding characters. All right, so, ooh, what's that? So let's get rid of that. All right, so that compiles. And so, this was A, which is declared as char A9. This is the one that was declared as char star, and this is the one that was declared as char C9 and used the standard array initializer. So, one thing you can see, all of them end up containing this sequence of characters, but they're in different locations. So A and C have ended up pretty close together, okay? Which suggests kind of that they're part of the same environment. And we'll go back and have a look at the program. In fact, they're both local variables for the main program. So they've ended up on the stack, in the stack frame for the main program. B, which is the char star referring to a string constant which I said would be located in the data area of the program's memory, has ended up in quite a different location. So that's kind of proving that initializer created a string in the data area. The other initializers simply filled up the values, filled up the elements of an object that was declared locally and ended up on the stack. Right, so you can have a look at those and have a think about why those numbers come out the way they do. As far as creating arrays, they're just like other variables. You can either get them created automatically by declaring them as local variables, in which case, when the function containing them is called, they come into existence on the stack. When the function containing them exits, they vanish from the stack. So that's automatic creation. In fact, if I remember, I don't know if it still exists, there used to be a keyword in C, automatic, and you could declare your local variables as automatic. But that's the default behaviour, so no one ever writes automatic. So once again, to point out the difference between these two, here a chunk of memory is allocated, a chunk of memory to store 9 char values is allocated in main's stack frame. For this one, there's no array, there's simply a pointer, a character pointer, which is 4-byte quantity, which has to be made to point to an array. Now I could have said str2 is assigned to str1. That's an interesting point. If I say str2 is assigned str1, then all that's happening is I'm copying the address of the first element of str1 into str2, and effectively str1 and str2 refer to the same object. And I could use them both the same. Now that's generally not a good thing to do in programming, is to have two different variables referring to the same thing. Because you've got an alias and you might change one, thinking it's not going to have any effect on the other, but it clearly does because they're actually referring to the same thing. In any case, so if you want to allocate an array, you can either do it automatically like that, or you can use malloc. So that's going to allocate 20 bytes of space, which is clearly going to be big enough to hold that string. And now I'm copying the contents of that string across from str, all right, from str1, that should have said, into str2. When I do this malloc, what's the contents of str2? If you want to talk about the contents of str2 as being the value of the variable str2, it's going to be a pointer into the heap where 20 bytes have been allocated to contain an array of chars. What's the contents of that array? Nothing at this stage. It only gets populated, or at least part of it gets populated, when you do that. And as I said, that should have been str1. And you can copy and paste that into something and compile it up and run it, and you'll see what's happening. And in particular, you'll see that the address of str1 is a high value on the stack. The value stored in str2 is, or the address, this is slightly misleading, because the address of str2, if I was to ask for that, is on the stack. The object str2 is on the stack, in the stack frame for the main program, but the thing str2 is referring to is an address in the heap. So what you'll see here is quite a different number to what you see here. Here you'll see 7f blah blah blah. Here you'll see something much smaller and 7f. And of course, you should always free up stuff for your malloc, even though I forget to do it half the time in the lab exercises. Right, next kind of data structure that we might be interested in playing with is structs. So arrays are pretty straightforward. They're just a sequence of elements. All the elements are of the same type. Structs are distinctive from that in that they contain a sequence of components, but the components can all be of different types. And rather than referring to the components using an index like you do with an array, you refer to them by name. So here's an example. We're defining a struct type which has integers, 2 character arrays, a single char value, and a value which is some other kind of struct. I haven't bothered to specify date, but you can probably see it's going to have year, month, day in it. And here's a particular instance of that, nothing to do with me. These values do not represent the real values associated with me in any way, except the birthday. You can send me birthday cards on the 12th of February if you like. Right, so hopefully we all understand that, how that works. One thing about this, well, I can't highlight it. That underscore student thing is called a tag, and the combination of struct and the tag is effectively a new data type. So it's a data type you've created without having to use typedef, but of course you can if you want to. You know, I could easily wrap typedef struct underscore student blah 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 student, and then I'd have the data type student. Now, with an array, there's clearly a notion that there's a sequence of values. There's a first value, a second value, a third value, a fourth value, and so on. In the case of a struct, we don't really have that notion. We've got a collection of values, but there's no inherent order amongst the values that are stored in the struct. So it could be implemented like that. Well, there's no reason why it couldn't be implemented like that. As long as you know where the individual components are, that's fine. You use the name, and that'll take you to a particular point in the struct, and there you'll find the value that you're looking for. So effectively what ends up happening, we're going to see this when we look at compilers and the way they the way they produce code for various kinds of things, that effectively the name of a struct component turns out to be an offset into the struct object. So it's simply a byte offset into the whole thing. So we've got a big chunk of bytes that represents the struct. The name corresponds to a particular, if you like, byte index into that struct. So in this example over here, the offset of the ID value would be 0 because it's right at the start, and that occupies 4 bytes. So the next field, the given field, starts at offset 4. That occupies 50 bytes. So the next field will start at offset 54, and so on, and so on. Okay. Now I'm talking about offsets. I'm talking about byte addresses. Typically a struct will start on a 4-byte boundary. And so, because we have to worry about alignment, then it's possible that we might end up with some wasted space inside our struct. And then the order that you define things in the struct is important in the amount of space that the struct is going to occupy. So here's a version of a struct with a compiler that simply puts the components of the struct in the order that they're specified by the user. So this single char goes first. The next thing in the struct is an int. We can't put the int directly after AA because that would put us on an odd byte boundary, and int values can't start on an odd byte boundary. So assuming that the struct started on a mod 4 boundary, then we have to have 3 bytes of padding so that the next component can start on a 4-byte boundary. Okay? So that would be the kind of thing we'd end up with, and you can see 1, 2, 3, 4, 5, 20 bytes required to represent that thing with 5 fields. If we had a smart compiler, and some of the compilers are smart, not sure about GCC or DCC, but you could easily envisage rearranging the order that components are stored in the struct to minimise the amount of wasted space. So if we put those 2 ints first, then fine, they can be adjacent to each other, no padding required. And then we can put the 3 characters at the end, and all we've got is a single unused byte right at the end of the struct. So dumb compilers will pad, even dumber compilers won't pad, and then you'll get alignment errors if you put BB starting at that address. But compilers are going to produce correct code, will do something like that. Some kind of compiler that optimises data structures might rearrange the fields like that. And the only difference this is going to cause is that BB, rather than being at offset 4, is now at offset 0. DD, rather than being at offset 4, 12, is now at offset 4, and so on and so on. So all we're really doing by this rearrangement is just changing the mapping between the field names and the offsets inside the struct object. Right, so I thought, let's see how a compiler would really do this. So here's a struct where you can see we've got lots of individual chars, lots of different kinds of data types. Oh, I should have put char f in front of the integer anyway, it doesn't matter. And here we've got another struct that's got different kinds of values in it as well. So let's see if we can work out whereabouts the fields are located inside the struct. Okay, so there's our structs. So there's an instance of the struct type underscore S1, there's an instance of the data type struct underscore S2. Okay, remember that's the type, that's a variable of that type. And maybe confusingly I've given them similar looking names, but they're quite different. In fact, the C compiler is smart enough to recognise that even if I called this thing S2 and I wrote struct S2, S2, it would understand that the first S2 was a struct tag and the second S2 was a variable name. So I wouldn't get confused. But as a programmer, we might get confused by that kind of thing. Could I? Oh, I don't know. Let's see. So you want to do something like this. And then, oh, good question. Let's see. Someone done it already. Happy enough? So, I mean, it ought to be able to work that out because it's looking for type names. It's scanning through a list of declarations. So each declaration is going to have a type followed by a variable name. And, if it's an array, it'll have other stuff. But it should be able to recognise after that semicolon, if I see something that I can interpret as a type name, then that's all right. But now we're getting into the realms of the obfuscated C code contest. So I will at least back up that much. All right, so how do we work out the offset? We know the address of the start of the object. So the very start of S1, ampersand S1, gives us a pointer to the struct. If I want to work out how far into the object is the field A, then if I get the address of the A component of S1 and I subtract it from the start of S1, then that should give me the offset. Okay? And I'll print that. And when I first tried this, I put %D, but then it whinged at me and said that it was actually a long, so I had to put LD. I'll show you that. Okay, so it seems that if you're taking the difference between addresses, then it's actually type long rather than type int. Which is interesting because I think I checked yesterday and long is the same length as int. You have to do long if you want to get a 64-bit quantity. Anyway, that will keep the compiler quiet. Okay, so S1 is at this location here. Once again, you should recognise that it's a very large address, therefore it's somewhere on the stack. A is at the start of the structure, B is at offset 8, C is at offset 12. Let's have a look at the code and see if there's anything surprising about that. Maybe. Okay, A is at offset 0, and then we have 6 chars. Then B was at offset 8. So clearly what's happened is the compiler has decided to add in 2 extra bytes of padding after the A field. So I can start B on a 4-byte boundary. And if I was to keep checking out fields, let's just find out where the D field is. Does anyone have a smart way of iterating through these things without repeating the code? If could do that, it'd be interesting. This is why arrays are nicer to iterate through. I think we got one more. So we really should be looking at this. Okay, so the first component occupies 6 bytes. The next component is an int, has to be on a 4-byte boundary. Therefore, we have to do some padding. Actually, interesting. Right, I'll just run this one first, and then I was going to change the order of B and C. So see if it realises that it can slip C into one of those spare bytes. But in any case, let's have a look at this. Okay, so B at offset 8. B is an int, therefore you'd expect the next component to start 4 bytes after that, which it does, 12. Then D starts 4 bytes after that, even though C, if I remember, is a single byte quantity. Okay, so we've got some padding there as well. D was, I should have printed the type, shouldn't I? D was a double, okay? So, D was a double, so double occupies 8 bytes, so you'd expect the field after the double to be 8 bytes further offset. And then I think that was an int, so it's a 4-byte quantity, so you'd expect the next field to be there. Now, let's fiddle around with the order of it. Let's see if that makes a difference. Obviously, programming with this struct, having made these changes, it looks exactly the same. You can still say s1.c, you can say s1.b, so you wouldn't have to change the code, even though you've actually changed the internal structure of the object. Oh, okay, good. All right. Let's just see this one first. Yeah, okay, so it has been a little bit smarter here. C is now at offset 6, so it's realised, okay, I've got 6 chars, then I've got another char, so I can stick that in the next byte. But then I can't start the next component, which is an int, until a 4-byte boundary, so I have to put in a padding byte. So what was their option to do optimising? -03, was it?
I think it's dash capital O.
At all? Oh, okay. Yeah. Now let's put these back and see if it's smart enough to do something. Good. All right, one of those, go and look at the C manual and you can find out what all those optimization levels do. But compiler dependent, whether it can optimize those, optimize the padding. And so you can see that the way structures are represented in memory may have wasted space. All right, everyone's off, so let's go.